Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Artificial Brains and Mathematical Artificial Neural Nets. A New Vision of the Artificial Intelligence. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. Engineer Jesus Velasquez Bermudez wants to make it clear that his knowledge in neuroscience is very limited, and that therefore inaccuracies can be found in some concepts of this presentations. Its knowledge comes from the serious study of many scientific works of experts in the field, which have helped to visualize what is presented here. On the other hand, it is also made clear that Engineer Velasquez Bermudez is not an advanced expert in traditional artificial neural networks. He understands them properly. The vision that prevails is that of a mathematical modeler, with extensive knowledge of the appropriate mathematics to perform this work. The list of short introductory lectures to decision-making artificial intelligence are presented in the picture. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart physical systems. Human knowledge is supported by two types of models. Mental model, it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all humans. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand mathematics, and to handle it, does not extend to all humans. It is necessary to acquire knowledge and experience, to handle this intelligence properly. At present, its development is directly related to the ability to handle computational and mathematical technologies. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows him to perform the analyses to understand and discover the models that govern the universe that is written in the language of mathematics, Galileo Galilei. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic of humanity. In practice, very few humans have this ability, and discipline. Mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing, and evaluation of eventual, and systematic, experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example, identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Mathematical intelligence and decision-making. Decision-making process is the final objective of any person or organization, which seeks to make the best decisions from its point of view, its criterion. This process, when carried out in real time, requires a great capacity for mathematical calculation, to handle the complexity of the real world, which increases over time, since the universe increases its entropy at each moment. When humanity began its evolution, it only had mental models to support its decisions, which seriously limited the speed of the evolution of the species, due to the little, almost zero, capacity of mental models, which led the human being to make decisions with very few calculations, or without them. Thanks to analytical intelligence, human beings developed their mathematical intelligence, which has led us to Industry 4.0. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. Then, the starting point of the name of artificial intelligence is associated to the pattern recognition. Today, the association is direct, and it seems that artificial intelligence is reduced to this function of the human brain, what has concentrated great amount of scientific research in working in this direction, forgetting other human brain functions. It seems that artificial intelligence is reduced to the emulation of mental intelligence, whose function is little known and explained. That is why it is known by scientists, that neural networks can predict how a system will behave, but that in general the parameters found cannot be explained, they have no clear content, just as the humans cannot explain how this function works in the human brain. But this approach cannot be said to have been unsuccessful, as it effectively and massively replaces activities that ordinary humans did not think machines could perform. At first, neural networks were aimed at finding ways of connectivity of artificial neurons, seeking to improve the results of prediction. Something like a statistical model in which many algebraic models are tested, until a good solution is found. Little has evolved to try to explain content in this connectivity. This is the case with GPT. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for Conda, text digesting, content generation, and search bots. But their ability to solve real decision-making problems, different from advanced pattern recognition, is minimal, if not nil. For many data scientists, data-oriented models are the only artificial intelligence out there. This includes academic teaching. This entails a problem of development of artificial intelligence, since many executives and managers not experts in AI, think that the only artificial intelligence that exists is predictive. Then, it is applications such as ChatGPT, and the like, that will be considered the AI of the future. The displaced methodology is formal mathematical modeling using algebraic equations, and/or differential equations. This is related to the use of mathematical programming, or optimization, to support decision-making. It is easy to show that in most companies, mathematical programming is not considered to produce knowledge, like the human. This is because decision-making does not concern researchers who promote artificial intelligence. Practitioners, perhaps fanatics, of traditional AI, have classified mathematical programming algorithms as the exact methods, not with the intention of highlighting them and promoting their learning. On the contrary, they disqualify them because in theory they cannot be used. But this is false. Thus, with the aim of repeating patterns, several meta-heuristics have been created trying to perform optimization processes, supported by very weak mathematical laws, which simply rely on imitating patterns of behavior of smart beings. But thinking, what to imitate ants, or whales, etc., produces better, or equal, results than optimization based on mathematical laws, is like expecting that these beings had discovered the theory of relativity. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. Lagrange's work is absolutely sound, based on formal mathematical laws, and not based on the observation of mental models of special smart animals. But their knowledge involves formal, and not just superficial, study. To think that a real-world problem can be solved better by a meta-heuristic, faster, more precisely, and closer to the optimum, than an exact method, is utopian. Although in its beginnings traditional artificial intelligence did not look at neuroscientific studies as a fundamental support, there are currently clear trends of recognized researchers, who consider that neuroscientific studies should be the basis for understanding the functioning of neural networks and the brain. Two of these researchers are Geoffrey Everest Hinton is a British-Canadian cognitive psychologist and computer scientist, most noted for his work on artificial neural networks. Hinton is considered as a godfather of artificial intelligence, having championed machine learning decades before it became mainstream. Recently, in a CBS chatbot, Hinton said that for several decades, he has been more interested in understanding the functioning of the brain than in building artificial intelligence algorithms. And Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. Hawkins is an American businessman, neuroscientist and engineer. He co-founded Palm Computing, where he co-created the Palm Pilot and Treo, and Handspring. He subsequently turned to work on neuroscience, founding the Redwood Center for Theoretical Neuroscience in 2002. In 2005 he founded Numenta Incorporated, where he leads a team in efforts to reverse engineer the neocortex, and enable machine intelligence technology based on brain theory. He is the co-author of On Intelligence, 2004, which explains his memory prediction framework theory of the brain, and he is the author of 8,000 Brains, A New Theory of Intelligence, 2021, based on his research in neuroscience. As a result of his studies, Hawkins proposes the hierarchical temporal memory, HTM neuron, that is a biologically constrained machine intelligence technology, and the sparse artificial intelligence model. One of the most famous neuroscientists, Santiago Ramón y Cajal, was a Spanish physician and scientist, specializing in histology and pathological anatomy. He shared the Nobel Prize in Medicine in 1906 with Camillo Golgi, in recognition of his work on the structure of the nervous system. Through his investigations into the mechanisms governing the morphology and connective processes of nerve cells, he developed a revolutionary new theory that came to be called the neuron doctrine, since brain tissue is composed of individual cells. Humanist, as well as scientist, he is considered the head of the so-called generation of sages. He is frequently cited as the father of neuroscience. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence, the knowledge created by scientists, and the way to produce it is part of today's human intelligence. Proof of the above is the speed with which we produce knowledge. It took many centuries, hundreds, to produce algebra, but mathematical knowledge every day occurs faster, and extends its borders, for example since 1947, with the appearance of the digital computer, a new science has been created, mathematics for computers, first monoprocessors today parallels. This must be part of the artificial intelligence of the future. When the previous trend changes, humanity will have begun its disappearance process. Artificial brains and augmented artificial intelligence. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial Neocortex plus Artificial Hypothalamus plus Artificial Hippocampus. This evolution may be summarized as the shift from artificial intelligence to augmented artificial intelligence, that evolves from artificial intelligence very powerful in pattern recognition, to intelligence that powers the human brain, becoming an exobrain with high decision-making capacity, in real time, and autonomously. Augmented artificial intelligence will be the new era of artificial intelligence will be based on the study of the operation of the neocortex and the real-time communication between algorithms, or cognitive robots, to build networks of mathematical models, that allow organizations to act in a similar way to the human brain, making intensive use of distributed processing. The Decision Support Systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models, that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of autonomous real-time distributed optimization, an artificial hypothalamus is obtained. Autonomy implies that models can act independently, without the involvement of a human command, and in real time, which can happen at any time. The concept of distributed optimization is associated with models that represent different agents, and that working as a team, solve a common problem, running in parallel. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. That resumes the knowledge of Lagrange for mathematical optimization. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Artificial intelligence and computer power. When formal mathematical models of real systems are known, the inability to use them, in human everyday life, is directly related to the very low speed of mathematical calculation that humans have, which does not allow the scientist to solve in real time the mathematical problem associated with the knowledge that he has. For robots, computer technology has overcome this inability, allowing them to solve in real time increasingly complex real problems. Only when humans will be able to bring the mathematical calculation power to the human brain, we can use the known mathematical models in human everyday life. However, organizations can already build their own artificial hypothalamus, using existing computational power. The power of artificial intelligence that we can use depends on the support network in the cloud, the local PC that serves as the user interface, and the power of the algorithms that are in the cloud and in the PC. If you want to implement powerful AI, you need to understand informatic, algorithms, and computer programming. The success is directly related to the ability to implement first and second level algorithms. Nowadays, the computer system is very complex and is part of the success. For example, Geoffrey Hinton, in the CBS chatbot referred previously, indicated that if, in 1986, he had tried to solve the problems that we can solve today, he believed that the computer used in 1986 would not have solved the problem yet. A small example of the power of computation is the case of regression models, which comes from genetics and was popularized by Sir Francis Galton in the late 19th century, with the publication of Regression Towards Mediocrity and Hereditary Stature. Today it is one of the fundamental techniques of predictive AI, parameter identification, but its concepts and limitations have not changed. They are: the number of observations must be greater than the number of parameters to be adjusted. The greater the number of parameters, the better models are generated in terms of goodness of fit, and if the number of observations is greater than the parameters, there will be redundant observations, which if used in the regression will produce confusion in the results to be obtained. In the origins of computing, the problem was the observation storage capacity, the power required to execute the process, that depending on the methodology, requires the inversion of a matrix of the size of the observations. With these constraints, estimating a model of thousands of parameters was a challenge. With the progress of computation, also evolved methodologies, estimation algorithms, until today to the conjunction of computing power and algorithmic power, which gives direction to the effective application of GPT models, which in practice permanently estimate models of hundreds of thousands, or millions of parameters. In the same way, will grow the power of prescriptive AI. Monolithic mathematical models. With the advent of the digital computer, in 1947, computer-oriented mathematics, and the first digital mathematical models were born. These models, due to the initial limitations of computers, were thought monolithically to be solved in computers with a single processor. This quickly exhausted the dimension of problems that could be solved. Atomized mathematical models. At the beginning of the decade of the 60s of the last century, the researchers presented the first works aimed at dividing the monolithic models, to convert them into modular, atomized, models. In the opinion of the speaker, this effort was made to get models more manageable, which resulted in lower memory requirement, and faster solution of mathematical problems. At that time, there was no parallel computing. To visualize the difference between the information provided by a monolithic model and an atomized model, we can think of a medical examination based on a photograph, and one based on an X-ray. Photography does not allow us to understand what is happening inside the human body, X-ray does. That is an advantage that cannot be achieved with a monolithic vision, which only provides aggregated information. Atomization allows to understand how a system is assembled, and how information flows inside. Parallel computing. The evolution of computers, from the single-processor computer, to the multiprocessor multi-core computer, opened the way to large-scale methodologies towards parallelism, since the mathematical bases were already implicit in all the works of Dantzig, Wolff, and Benders. Today, they become fundamental methodologies, since the computers that are most used are multi-CPU and multi-core. Additionally, connectivity between computers turns the limits of parallelism into an infinite number of possibilities. This gives the opportunity to the birth of artificial brains. All the developments, in mathematics applied to solving real-life problems, converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing, and cloud computing, to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. From human brains to artificial brains. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. The connection between all the subsystems, within and between them, is made by bioneurons. For this, biological neural networks are formed, through which information flows in the brain, and in general in the human body. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. Hippocampus store the experience and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus, where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. The operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge: formulation, the components of mathematical models, and historical data of the results generated solving the mathematical problems, using large-scale optimization methodologies. This information is used as starting point in future uses of mathematical models to support decision-making. Sparse artificial intelligence. This section is based on the paper "Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World." Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. Sparse artificial intelligence. The Hawkins network model introduces a new feature in cortical columns that proposes that a representation of location calculated within the subgranular layers of each column. The representation of location is relative to the object being sensed. Pairing sensory features with locations is a requirement for modeling objects and therefore must occur somewhere in the neocortex. Hawkins proposes it occurs in every column in every region. The network model contains two layers and one or more columns. Simulations show that small single-column networks can learn to recognize hundreds of complex multidimensional objects. Given the ubiquity of columnar and laminar connectivity patterns, the columns and regions have more powerful recognition and modeling capabilities than previously assumed. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. In summary, the modeling of the structure of neocortical regions is organized into columns and layers. Connections between layers run mostly perpendicular to the surface, suggesting a columnar functional organization. Some layers have long-range lateral connections, suggesting interactions between columns. Similar patterns of connectivity exist in all regions, but their exact role remain a mystery. All regions have a motor output. Hierarchical temporal memory, HTM, is a biologically constrained machine intelligence technology developed by Numenta. Hawkins' work gives rise to the HTM neuron, that is intended to emulate the overall structural and functionality of the human neocortex. The main properties of HTM is hierarchical structure, sparsity and modularity. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. Thousand brains theory. Another important contribution of Hawkins is related to the multiple brain models of the same object working cooperatively. For example, to recognize an object, 5 models of that object can intervene, each of them generated by one of the senses that the human being enjoys. Complete knowledge occurs when the knowledge generated by all models in all layers are integrated. Thousand brains theory of intelligence implies multiple models of an object, each model depends on a point of view. All models work cooperatively to identify the object, or situation. The identification starts from the sampling process, and progresses until it finds that all the models converge, that is, they agree, and at that moment the object, or the situation, has been identified, and the process is done through the flow of information in the neocortical regions. Mathematical revolutions, from arithmetic to parallel thinking. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Mathematical revolutions, from arithmetic to parallel thinking. A brief history of mathematics, focusing on the evolution of optimization applied to real-world problems. The evolution of mathematics has allowed us to better understand systems, evolving from monolithic to large-scale modeling. Those interested can watch the video. Mathematical revolutions from arithmetic to parallel thinking. Large-scale mathematical model structure. The solution of an optimization problem using large-scale methodologies is based on partitioning the problem into 2 sub-problems that must be solved in coordination. It can be said that there are 2 basic methodologies that bring together majority of applications: Bender's partition theory, BT, and Lagrangian relaxation, LR. They can be considered complementary. In BT, the partition is performed according to the variable's type. It is a primal method that works on primal feasible zone. In LR, the partition is performed according to the constraints type. It is a dual method that works on dual feasible zone. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Bender's partition, or Bender's decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in all real applications. The large-scale methodologies allows to divide a monolithic problem into multiple problems that can communicate to each other. Partitioning and decomposition divides the problem into multiple subproblems, represented in the diagrams by colored submatrices, which link them to subproblems. Depending on its complexity, the ways to divide a system may be non-numerable. In the image, the green diagram corresponds to the matrix, and the blue diagram to the associated hierarchical structure. The diagram shows a 2-level structure. This diagram shows a 3-level structure. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The hierarchical structures produced by large-scale methodologies do not simply correspond to mathematical artifices to solve large-scale problems. These structures are linked to representations of reality. To model a real system, two visions are possible. Top-down implies a monolithic vision, based on sequential synchronous mathematics. From the bottom up, a parallel atomized vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. This hierarchical approach can be changed by the vision of an artificial hypothalamus, in which the problems work cooperatively, and have a protocol of communications between them, to solve a common problem, running in parallel. The mathematics to solve these multi-problem parallel processes are already developed and proven. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Velázquez Bermúdez has written several papers contain information related to the solution of large-scale mathematical problems, using decomposition and multi-level partitioning, Bender's partition theory, Lagrangian decomposition theory, cross-decomposition, and asynchronous parallel optimization. The documents cited can be useful for working on large-scale mathematical modeling. Neocortical regions and large-scale mathematical structures. In optimization models, it is common to use a matrix that relates columns with variables, and equations with rows. Structurally similar to that of the human cortex. The structures that can be produced can have any topology, like neocortical structures. However, it should be noted that while in neuroscientific studies, topology is not clearly explained, but in the case of large-scale mathematical structures, topology is defined by mathematics, and not by human interpretation. In a multi-level mathematical model structure, the different levels can be characterized by the type of processing they perform. Large-scale methodologies generates three processing areas. Holistic, that coordinate all processes and solves the problem. Communicative, all intermediate layers responsible for adjusting the information that is transferred between the uppers layers and lowers layers. Sensitive, intensive in generating basic information that produces the data that is processed in the upper layers. In dynamic systems it should be related with time dimension. When simple problem division methodologies are applied, verticalized structures are obtained, that ignore the transfer of horizontal communication. That is, use only Bender's theory, or only Lagrangian relaxation. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. Everything indicates that the structure, and joint functioning of the neocortex and hypothalamus, is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. When comparing the human cortical structures with cortical structures of animals, it has been found that the complexity, number of layers and columns, increases with the intelligence of the living being. This is consistent with the fact that, the greater the complexity in the structure of optimization algorithms, speed off the solution time, and produce greater the understanding of the problem being faced. But it implies greater complexity in the mathematical aspects, which fortunately is manageable with the actual level of computer technology, always growing. Artificial neural nets and mathematical artificial neural nets. Traditional artificial intelligence, based on artificial neural nets, ANN, and support vector machines, SVM, has concentrated its efforts on imitating the mental models of human beings in the recognition of patterns. Modeling efforts, coupled with today's great computational power, have enabled a great development in pattern recognition. definitively surpassing the human capacity for such activity. However, being a mental intelligence older than mathematics and creative, which has grown in the human being based on elements other than science, closer to empirical evidence, these characteristics are transferred to the scientific process of creating an artificial intelligence oriented to mental intelligence. Because of this, its growth has been slower than it would have been if we had a scientific basis for mental intelligence. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. Convolutional artificial neural nets. They correspond to ANNs specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. Convolutional artificial neural nets. They correspond to ANNs specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built based on mathematical models that represent a system, and that it does contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. An artificial hypothalamus is a network of mathematical artificial neurons. Each of them represents a system or subsystem. The difference with large-scale methodologies is that the solution is visualized as specialized communications between mathematical problems, while in the artificial hypothalamus the process is cooperative based on autonomy, distributed, and real-time processing. In addition, there is a standardized language for communications between mathematical artificial neurons. Any type of organization can be represented following these principles. The case of a poultry production system is presented. The system has been divided into 6 subsystems, which together make up the poultry production system. Thousands of brains and artificial brains. A monolithic model can be associated with neocortical regions. Using large-scale methodologies, the monolithic model can be visualized as a network of mathematical models, or artificial mathematical neurons. The way to connect the network of mathematical models may be associated with the way cortical regions are divided. Hierarchies can be associated with multiples views of the same system, as proposed by Jeff Hawkins. It seems normal that, to recognize the pattern of physical objects, the 5 senses are used, each of which will have its own model, and working cooperatively all identify a unique object. If we assume that reality has several important points of view, one of them should be selected as the main one. The problem of his choice must be faced. This is to define which is the best hierarchy to use. Considering the vision of large-scale optimization as multiple points of view, High developed the Bender's multi-decomposition methodology. In simple multi-level Bender theory, in many cases there is no obvious hierarchical order for partitioning. MBD is a new approach that takes advantage of formulating multiple equivalent problems, one for each point of view, and formulating an extended coordinator model that integrates all points of view. Thinking in the thousands brain of Hawkins and consider a global multi-business company in which the general control of the company is carried out through the board of directors. For directors, 3 points of view are the most important. The company operates in 3 markets: electricity, gas and oil. operates in several regions, and administratively is managed in several departments. From the point of view of traditional partitioning methodologies, such as standard benders, you need to choose a point of view, a criterion, to begin the partitioning process. In this case, there are three possibilities. The partitioning process implies that the problem from one point of view is represented with several models, depending on the number of entities that make up the point of view. For example, for business case, 3 models are required: electricity, gas and oil. Partitioning and the decomposition of a system can occur in multiple ways, without there being a mathematical reason to select one as the best. The diagram presents a system that can be sorted hierarchically by 3 alternative criteria: business, regions, and functions. Alternatively, it is possible to choose another hierarchy: regions, business, and functions. It is important to note that in both cases it is met. The last layer, the sensory one, is the same since it corresponds to the atoms of the system. These could not change according to the point of view. The upper layer, the coordinators, is partially the same, since in each of them, the information corresponding to the alternative point of view is missing. The advantage multi-decomposition arises when subproblems are solved based on an asynchronous parallel approach. In this case, each time a problem is solved, a cutting plane is included in the coordinator problem, in such a way that the number of mathematical elements included depends on the optimization process, the number of cores used, the numbers of vision of the system, and the structure of each of the subproblems. To solve complex mathematical optimization problems associated to large enterprises, the optimization problem may be decomposed using different point of views. In many cases, there is no obvious hierarchical order: first business after regions and finally functions, or first regions then business and finally functions, or the algebraic formulation depends on the hierarchical order, but the optimal solution must be the same regardless of the point of view. Then, it is possible to modify the standard large-scale methodologies. All models refer to the same system, or firm, and are therefore equivalent. Then, it is possible to modify the standard large-scale methodologies to simultaneously handle all the models, and improve the solution of the integrated problem. The 3 models can be integrated to include mathematical elements from the different points of view, and they could speed off the solution process, and to have a better vision of the system. The artificial hypothalamus can be extended to handle all the problems that are generated as a sequence of the multi-benders decomposition implementation. For those interested in learning more about this topic are invited to watch the video. Artificial hypothalamus and multi-benders decomposition. Artificial hippocampus, a mathematical models expert systems. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. Mathematical modeling expert systems. A knowledge-based system, KBS, must store 2 types of knowledge: mathematical components, equations, problems, models, previously used and working properly. This information is generated by the modeler who builds the mathematical models and their entire operating environment, and results of previous runs to speed up the solution of new problems. This information is generated by the math models when they are used, and correspond to the trajectories of the variables involved in these models. The use of this information is totally dynamic, since it depends on the value of the input parameters in each new run. Artificial hippocampus. Storing mathematical components. Optex, HI's artificial intelligence to develop artificial brains, manages the artificial hippocampus. It is oriented to make high-complexity large-scale mathematical models without programming. The models are built in a modular way, as if they were a Lego set, which are formed by a compatible system of equations, the Leo parts, for all models. When considering that an artificial brain will gather, in an integrated way, the mathematical models required by an organization, we must be aware that a traditional approach, based on programmers, is a very difficult path, if not impossible. As everything has evolved, HI has developed Optex, the artificial intelligence to produce artificial intelligence algorithms. The interested party is invited to watch the video. Making high-complexity large-scale mathematical models without programming. Artificial hippocampus. Storing the history of runs. While mathematical models on digital computers, and the data storage disks, date back many years, more than 60 years, and despite the Industrial Revolution 4.0, how to run a model, it does not seem to have evolved. The normal process is: the model is thinking monolithically. A high-performance solver is selected to solve the problem, and the results are post-processed, and the results of the models are stored, with administrative purposes. Usually, in the next run, the model starts from scratch, ignoring the past, that is, it has no memory. In some cases, it is heated from a starting point provided by the last run, presumably the last optimal solution, or a point that ensures feasibility. However, an artificial hippocampus, designed for the artificial brain, can take advantage of a lot of information produced within a run, and during the history of all runs. Two examples will be briefly presented: handling of Bender's theory, and generation of convex hull. Following the principles developed by Bender's, it is possible to build an artificial hippocampus that remain active, and useful, beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. An artificial hippocampus stores cuts from one run to be used in the next, which will produce new cuts. HI is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. The process is similar for Lagrangian relaxation. Another alternative to generate knowledge, that is stored in the artificial hippocampus, is the generation of convex hulls, associated with optimal solutions of the mathematical problems. The multidimensional grid that represent the convex hull can be incorporated into the integrated problems, to accelerate the solution process. Depending on the specific problem, the convex hulls may be permanent, or they must be recalculated dynamically when the parameters of the mathematical models change. Convex hulls allow flexible approaches, as in the case of an energy transmission system, in which they can be associated to two different ways to solve the problem: flow AC and DC flow. The production of convex hull of optimal points is a standalone process, therefore they can be generated outside the optimization process. Real-time smart and autonomous communication between robots. The central part of an artificial hypothalamus is the formalization and the standardization of a math language between cognitive robots, to be used as the way to communicate multiples math algorithms. The core of this language is the duality theory, that support the mathematical programming algorithms, that may be developed using the concepts of large-scale optimization methodologies, to solve high-complex math models based on the partition and the decomposition of the real-life complex systems. An artificial hypothalamus corresponds to a superalgorithm that coordinate multiple cognitive robots that operating simultaneously, autonomously, in real time, acting as the human hypothalamus, to achieve a common goal. By joining all the concepts presented here, it is possible to define a language between robots, math problems, algorithms, or agents, based on an exchange protocol of information between the multiple types of problems, in which any pair of robots communicate by exchanging the information produced by each of them, which is synthesized in the value of the primal and the dual variables that they produce. If each robot is identified by the R index, in each conversation step K, the actions of each robot are inputs, dual and primal variables that our robot uses produced by other robots. All the data available until the begin of conversation step K is characterized as the historic knowledge database QK. Outputs, primal and dual variables that produce the robot R, it can be characterized as XKR, PKR. Transformation function FRQK, mathematical problem that the R robot solves to produce XKR, PKR, starting with QK. Mathematically this is XKR, PKR, equals FRQK. QK equals QK minus 1 union with XKR, PKR, Q0 equals. When our robot receives information QK, it processes it, generating information, XKR, PKR, and a conversation step K plus 1. The robots receive, or search, the inputs produced by other robots, and produce the outputs to be used for other robots. The information produced is added to the historical, and it is stored in the artificial hippocampus, an intelligent database on disk, or in RAM, which can be accessed in the next conversation of all robots. Then, based on large-scale optimization methodologies, communication between robots is synthesized in the transformation functions FRQK and in the storage of all the information produced, XKR, PKR, in an optimization knowledge database, QK, which can reside on RAM disk, offline, or on RAM memory, online. In a static problem, frontier conditions fixed, when the coordinator robot detects that has enough information to establish the optimal decision, it proceeds to close the conversation cycle, and terminates the optimization process. If the problem is dynamic, frontier conditions time dependent, the robots will have a continuous conversation in order to keep the system as close as possible to the optimal decision path, which is not possible to obtain due to system uncertainty. This process, based on duality theory, is the support of artificial hypothalamus capable of processing the information required for Industry 4.0. Oil and gas artificial brains. Artificial brains examples. The interested party is invited to watch the video. Oil and gas artificial brains. Oil and gas artificial brains. Not every artificial brain should be for an organization. The cyclist's artificial brain, that could be built with $100, is an example of an artificial brain for a person, which must use the mental intelligence that he has accumulated. The goal is to accelerate the processes of calculation and data acquisition, to have a great journey. Specific objectives may be: minimize energy consumption for a fixed time, or minimize travel time for a predetermined distance. The artificial brain may consist of hardware, Hypnone, and CPU Yard. I/O Raspberry. Databases, traffic, climate, and terrain. Data acquisition, GPS, and a mathematical model. The image presents the artificial brain of the cyclist. Everything can be connected. Oil and gas artificial brains. Algorithms swarm. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Alice, which way I ought to go? The Cheshire Cat. It doesn't much matter which way you go, If only you walk long enough. Thank you for your attention.